The Milky Way is dying. Not quickly, not dramatically, not in any way that will matter to anything alive today or anything alive for billions of years to come. But the process has already begun, is in fact already well advanced. And the galaxy you live in, the galaxy that contains every star you have ever seen with your naked eye, the galaxy that has been forming stars for 13 billion years, is running out of the material it needs to continue. The death of a galaxy is not an explosion. It is not a collapse. It is something slower and stranger, and in some ways more unsettling than either. It is a fading. A galaxy dies the way a fire dies when the fuel runs out. Not all at once, not in a final burst, but slowly, over an incomprehensible span of time, producing less and less light as fewer and fewer new stars are born, as the existing stars age and die and are not replaced, until what remains is a vast dark collection of stellar remnants, white dwarfs, neutron stars, black holes, orbiting a galactic center in silence. The Milky Way's peak star formation rate was approximately 10 billion years ago. At that time, the galaxy was producing new stars at a rate roughly 10 times higher than today. Since then, the rate has been declining. Today, we form approximately 1 to 3 new stars per year. In 10 billion years, the rate will be a small fraction of that. The Milky Way is not at its beginning. It is not even at its middle. It is in its long, slow afternoon. To understand how a galaxy dies, you need to understand how it lives. A galaxy is not simply a collection of stars. It is a system, a gravitationally bound structure containing stars, gas, dust, dark matter, and the complex physical processes that connect them. Stars form from cold molecular gas clouds when those clouds become dense enough and cool enough to collapse under their own gravity. The stars that form burn through their fuel, produce heavier elements in their cores, and eventually return material to the interstellar medium through stellar winds, planetary nebulae, and supernovae. Some of that returned material is recycled. It cools, accumulates into new molecular clouds, and forms new stars. The galaxy breathes, inhaling gas from its surroundings, cycling it through stellar generations, exhaling enriched material back into the interstellar medium. But the cycle is not perfectly efficient. Some gas is lost. Some is heated to temperatures where it cannot cool and collapse. Some is expelled entirely by the energy of supernovae and active galactic nuclei, blown out of the galaxy in galactic winds that carry material into the circumgalactic medium and beyond. And the reservoir of raw material, the gas available to form new stars, is finite. The Milky Way formed from a large reservoir of gas approximately 13 billion years ago. That reservoir has been depleting ever since. Every star that forms uses up some of the gas. Every supernova blows some of it away. Every stellar generation leaves behind a remnant that no longer participates in the cycle of star formation. What remains in the interstellar medium is a fraction of what existed at the beginning, and it is declining. But the galaxy's death will not be peaceful. In approximately 4.5 billion years, roughly the same amount of time that Earth has currently existed, the Milky Way will collide with the Andromeda galaxy. Andromeda is the nearest large galaxy to our own, approximately 2.5 million light-years away, containing approximately 1 trillion stars compared to the Milky Way's estimated 300 billion. It is moving toward us at approximately 110 kilometers per second, not across our field of view, directly toward us, along our line of sight, on a trajectory that current measurements confirm will result in a direct collision. A galaxy collision sounds like the most violent event imaginable. Two structures, each containing hundreds of billions of stars, slamming into each other at over 100 kilometers per second. It is violent, but not in the way the word collision implies. Galaxies are mostly empty space. The stars within them are separated by distances so vast that two galaxies can pass through each other without a single star directly striking another. The probability of any individual star in the Milky Way colliding with a star from Andromeda during the merger is essentially zero. What collides is not the stars, it is the gas. The interstellar gas clouds of the two galaxies interact. They collide, compress, heat, and shock. The compression of gas clouds triggers star formation, a burst of new stellar births triggered by the merger, a brief flaring of star formation activity in a galaxy that is otherwise in decline. The merger also fundamentally disrupts the orbital structure of both galaxies. Stars that were on stable circular orbits in the Milky Way's disk are scattered onto new trajectories by the tidal forces of the collision. The neat spiral structure, the arms, the disk, the bulge, is torn apart and rebuilt over hundreds of millions of years as the two galaxies gravitationally interact, separate, return, and eventually coalesce. The end result, over approximately 6 billion years, is a single large elliptical galaxy, sometimes called Milkomeda or Milkomeda by the astronomers who study it, containing the merged stellar populations of both original galaxies, its gas largely consumed by the star formation burst triggered by the collision. Its structure transformed from two spirals into one featureless ellipsoid of aging stars. Our Sun will survive this, almost certainly, probably ejected from the disk by the tidal disruption, possibly in a new orbit that takes it far from the galactic center, but surviving intact. Earth, if it still exists, will continue orbiting the Sun through the merger. From the surface of Earth during the collision, approximately 4 billion years from now, the night sky will be extraordinary. Andromeda, currently a faint smudge visible to the naked eye, will grow over millions of years into a structure spanning much of the sky. The collision will produce vast regions of star formation, visible as glowing nebulae across the merged structure. The sky will be brighter, more complex, more visually dramatic than anything the current night sky contains. And then the star formation burst will end. The gas will be used up, and the long fade will begin. Elliptical galaxies are the graveyard stage of galaxy evolution. The Milky Way and Andromeda are both spiral galaxies, gas-rich, star-forming, actively cycling material through stellar generations. Elliptical galaxies are different. They are generally gas-poor, star formation-poor, dominated by old red and orange stars rather than young blue and white ones. They are the product of mergers, the remnants of galactic collisions that used up the available gas and left behind an aging stellar population with insufficient fuel for new generations. Milkomeda will be an elliptical galaxy. Its star formation will decline rapidly after the merger-triggered burst. Over billions of years, its stellar population will age. The massive blue stars, which live for millions of years and die in supernovae that briefly outshine the galaxy, will all be gone. The medium-mass stars, like our Sun, will have become white dwarfs. What remains, burning for billions of years more, will be the red dwarfs, the small, dim stars that burn so slowly they can last for trillions of years. The galaxy will redden, its overall color shifting from the blue-white of an active star-forming system to the red-orange of an aging stellar population, as the hot blue stars die and only the cool red ones remain. And slowly, the red dwarfs too will exhaust their fuel. Not for a very long time. The last red dwarfs will burn for trillions of years, tens of trillions in some cases. The Milky Way as it currently is will not produce its last stellar light for an incomprehensible span of time. But the last stars will eventually die. There is something that will outlast the stars. At the center of the Milky Way sits Sagittarius A, a supermassive black hole approximately 4 million times the mass of our Sun. At the center of Andromeda sits an even larger supermassive black hole, approximately 100 million solar masses. When the two galaxies merge, these black holes will eventually find each other, drawn together by the gravitational dynamics of the merger, forming a binary supermassive black hole system at the center of Milkomeda. The two black holes will orbit each other, losing energy to gravitational waves, the same type of waves that LIGO detected from stellar mass black holes in 2015, spiraling inward. Over hundreds of millions to billions of years, they will eventually merge, a collision of supermassive black holes that will release more energy in gravitational waves than any event since the Big Bang. The merged black hole, perhaps 100 million solar masses or more, will sit at the center of a galaxy that is no longer forming stars, a dark engine at the heart of a fading system. And Milkomeda's black hole will continue to grow, accreting any gas that falls near it, consuming any star that wanders too close, growing slowly over the trillions of years during which the last stars burn out, until it is surrounded by a halo of stellar remnants, white dwarfs, neutron stars, the corpses of 100 billion stars orbiting in the dark. Beyond the merger, beyond the death of the last stars, there is a longer timeline that belongs not just to the Milky Way, but to the universe. Dark energy, the accelerating expansion that is already pulling distant galaxies beyond our cosmological horizon, will eventually isolate Milkomeda entirely. The local group of galaxies, held together by their mutual gravity, will remain bound, even as everything beyond it recedes. But the galaxies beyond the local group, the Virgo cluster, the Coma cluster, all the vast structure of the cosmic web will recede until their light is too redshifted to detect.
Milkomeda will be alone, an island in an expanding void, the only galaxy in its observable universe, containing the stellar remnants of two galaxies that once shone with the light of hundreds of billions of stars. The white dwarfs will cool. Over trillions of years, over timescales that make the current age of the universe look brief, they will fade from white to yellow to red to infrared to nothing. Black dwarfs, dark, cold, crystallized spheres of carbon and oxygen, each containing the mass of a star, drifting in silence. The neutron stars will pulse more and more slowly as they lose rotational energy. Their magnetic fields will decay. They will cool, eventually indistinguishable in temperature and emission from the surrounding dark. The black holes will persist longest, slowly evaporating through Hawking radiation on timescales that dwarf everything else in this story, 10 to the 67th power years for stellar mass black holes, 10 to the 99th power years for the central supermassive remnant, radiating away their mass in the slowest, most patient process in the universe, and then gone. The Milky Way will end not in fire, but in the slow accumulation of silences. The silence when the last supernova occurs, the last massive star dying in the last explosion that illuminates the galaxy from within. The silence when the last red dwarf dims below the threshold of nuclear fusion and becomes a brown dwarf, cooling slowly. The silence when the last white dwarf cools to the temperature of the surrounding space, its crystallized interior preserving the chemical record of every star it burned through, radiating nothing. The silence when the last black hole evaporates, releasing its mass in a brief final burst of Hawking radiation that briefly illuminates an otherwise completely dark universe before the silence becomes total. The Milky Way is dying not quickly enough for anyone to notice. The sky you look up at tonight is the sky of a young galaxy, young in the sense that it still has billions of years of star formation ahead of it, still has gas in its disk, still has the collision with Andromeda to endure and transform it, still has the long twilight of red dwarfs burning for trillions of years after the collision. But the peak was 10 billion years ago. The rate of star formation has been declining for longer than the Earth itself has existed. The galaxy you live in has been in gradual decline before the first animal drew breath on this planet. We arrived late, not at the end, nowhere near the end by any cosmic standard, but late enough that the most productive era of this galaxy's star-forming life is behind it. Go outside on a clear night, far from city lights, and look for the Milky Way. It is best seen in summer in the northern hemisphere, a band of diffuse light stretching across the sky, the combined glow of billions of stars too distant to resolve individually, the disk of our galaxy seen edge-on from our position inside it. Every point of light in that band is a star, most of them hotter and younger and more massive than our sun, burning their fuel faster, dying sooner. Some of them are already dead. The light you see left them thousands of years ago, and the star itself has since become a white dwarf or a neutron star or collapsed into darkness. In the direction of Sagittarius, toward the galactic center, the band thickens and brightens. That is the core, the denser central region where stars are more numerous, where the supermassive black hole lurks, invisible behind clouds of gas and dust. And from a dark enough sight, a faint smudge is visible. Faint, barely there, requiring dark adaptation and averted vision. That is Andromeda, 2.5 million light-years away, moving towards us at 110 kilometers per second, the galaxy that will merge with ours and transform everything about the structure you are standing inside. The Milky Way is dying, but not yet. For now, it is still here, still forming stars, still cycling gas through stellar generations, still producing supernovae that scatter heavy elements across the disk, still gravitationally bound, still visible as a band of light across a dark sky. For now, it is still alive in every sense that matters. The fading is slow, the darkness is distant, and the sky tonight, this specific sky, on this specific night, from this specific planet, in a galaxy that has been forming stars for 13 billion years and has billions left to go, is extraordinary. Look at it while it lasts.